Yes, but what is useful about this way of thinking? Well, this way of thinking tells us that if we throw light horizontally instead of throwing a ball, then light will move straight, right, from side to side. However, since the elevator or the spaceship is accelerating upwards, the ray of light will approach the bottom, the floor of this spaceship in an accelerated fashion, in the same way the projectile did. Therefore, applying the same, so since this situation is indistinguishable to the presence on Earth or in any other place where there is gravity, we conclude that light also drops. Namely, light is deflected when passing near a mass as a pebble would, in the same way, except for the fact that light moves at much larger speeds, and therefore we see the deflection less. However, gravitational lensing, which is a consequence of light being deflected by the presence of mass, has been observed. Here you have, for example, a distant quasar, a very bright source, very far away, and the rays of light that should move straight are actually deflected by the presence, in this case, of a cluster of galaxies. And then you see multiple images arriving to us. Here you see multiple images of one particular quasar taken with the space telescope, the Hubble Space Telescope. Here you have another example. If the lensing object is just in the middle, intervening between the observer and the object whose light is being lensed, then the lensing happens all around in the same manner, and there will be a ring formed that is called Einstein ring. And here you see pictures taken of several Einstein rings. So these are images, modern images taken with modern telescopes, but actually gravitational lensing was what was used to prove the theory of relativity. So it was first observed during a total sun eclipse in 1919, and what was observed was the gravitational lensing or deflection of light due to the presence of the sun of stars that were near the sun. So as you see, the apparent position of the star moves upwards with respect to the sun, because the light is deflected. The angle was very small, and this could only be seen for light that passing very close to the sun, so one needed an eclipse. But in 1919, this was used as a confirmation. Now, although we can understand the effect using the equivalence principle, general relativity goes a bit farther. In the general relativistic explanation is actually that the presence of a mass, such as that of a star or a planet, etc., deforms space-time. And so it is the deformation of space-time that deforms or actually bends the path of particles which pass nearby. Here we have a demonstration which uses an analogy. In reality, we are speaking in general relativity of 4 dimensions, 3 spatial dimensions plus time, but here we have only a 2-dimensional demonstration. This is what we can see. So this black flat canvas or surface illustrates a region of a space-time in which there is no mass. no big mass deforming it. And so you can see that particles would move through this region in a straight path. Again, so straight path. However, if there would be a mass there, then the fabric of a space-time would be deformed by it, pretty much as it is in this case. So here we see, of course, the deformation would depend, the quantity of deformation would depend on how much mass we have. So for example, here we have a shallower potential well, which corresponds to a smaller mass than here. Here we have a much deeper potential well. But in both of them, then, the paths of particles would round. For example, this could be the path of the circular path or elliptical path of a planet next to the sun. And here we would have, for example, the potential that corresponds to a black hole, in which there is much more mass concentrated in a small region of a space-time. So a black hole is a mass so large, concentrated in a radius so small, that actually once particles or light get very close to it, nothing can escape, not even light can escape. So in general relativity, either particles, planets, even light follow as a straight a path as they can in a curved space-time. A black hole is so dense, it's a region in which the mass is concentrated in a very, very, very small region, that the gravity attraction becomes so strong close by that not even light can escape. However, for example, the mass of the sun should be concentrated in a radius of 3 kilometers. 3 kilometers is from here to Santa Monica, probably. So the radius should be this small. Instead of the 700,000 kilometers, the mass, the radius of the sun is now. If the mass of the sun would be concentrated in a radius of 3 kilometers, it would become a black hole. The mass of the Earth concentrated in 1 centimeter, in a radius of 1 centimeter, would become a black hole. So it has to become extremely dense. Now let us try to argue the way in which gravity becomes geometry. So free particles follow geodesic paths. These geodesic paths are the shortest paths between 2 points. On a plane, the shortest path between 2 points is a straight line. But on Earth, for example, if you can follow the path of planes that try to move in the straightest path possible on Earth between 2 points, this geodesic or straightest path possible, the shortest path between 2 points, are sections of great circles. So assume 2 particles A and B are initially moving parallel to each other on a plane or on a sphere. In the case of the sphere, they are both thrown northwards, and they keep northwards. Namely, they keep with a velocity which is always parallel to itself. So both A and B keep moving always in a straight path in the same direction. So on a plane, initial parallel paths continue to be parallel. So with a Newtonian gravity, we would say, well, there is no force attracting the 2 particles, and that's why they continue in a straight path. In general relativity, we would say this is a flat space-time, it's a plane, there is no curvature. Now, on the surface of a sphere, 2 particles that start always and continue moving north will approach each other. So from the point of view of Newtonian gravity, we would say, well, these particles approach each other because there is an attractive force between the two. From the point of general relativity, would say, well, the fact that the path of these particles approach each other is due to the curvature of the sphere. Now, we have talked about applications that are far removed from our lives. For example, gravitational lensing. But you could say, well, does general relativity affect my everyday life in any ways? And yes, it does. And for this, we have to understand the following effect. We are going to use again the principle of equivalence. So this is the equivalence between what would happen in an accelerated spaceship in the middle of nowhere where we can neglect gravity, and what would happen if this spaceship would be on Earth, just standing still on Earth. So let us consider two observers, A and B, one on top and the second at the bottom of this spaceship. This spaceship is accelerating upwards. The clock A throws pulses of light at regular intervals, for example, 1 second. So 1 second, one pulse, another pulse, another pulse. Because the velocity of the point at which of reception where B is always moving faster with respect to where A was when it was at the time it was emitted. So the velocity of B is always faster than the velocity of A at the point of emission, right? It takes a short time for the light to travel from A to B. In this time, the vessel has moved. So essentially, the next light pulse from A to B must go always less distance as the velocity is greater. So the pulses travel less and less distance, so they arrive faster. So the intervals at which B sees the rays of the pulses, the rays of light emitted by A, is shorter. So B sees the A clock as running fast. So the same thing applied on Earth. Clocks that are higher up with respect to Earth run faster. Now you can say, well, is this important for anything? This is very important for the global positioning system. So we have seen already in our special relativity class, global positioning system consists of a network of satellites that tell the position and time at regular intervals. So they say, at this time, I'm in this position. At this time, I'm in this position. Your global positioning system in your hand, in your car, receives these signals and then can figure out what's the position of the receiver. Now, the precision that we want from a GPS location is about 1 meter. So from that, we know the precision we need in time, knowing in how long light travels a distance of 1 meter, because the signals that are coming from the satellites travel at the velocity of light. So the distance of 1 meter divided by the speed of light, which is 300,000 kilometers per second, is 3 nanoseconds. 1 nanosecond is 1/1,000 million of a second. So this is the precision needed in time. Now, because the clocks on board of these satellites are moving faster, there is a special relativistic effect. Moving clocks run slower. So this is time dilation. And so it would, if not corrected for the special relativity effect due to the velocity, the clocks would accumulate 7 microseconds per day. A microsecond is 1/1 million of a second. That means it's a rather large error with respect to a microsecond. Now we can add also the general relativistic effect. because the satellites are higher up, they are at an orbital distance of 20,000 kilometers. Then they run faster, and this is a general relativistic effects. So in a day, without correcting for general relativity, we will have an error of plus 45 microseconds. And the special relativity, due to the time dilation of moving clocks, would get a correction of 7. They have opposite signs. This 38 microseconds per day cumulative error would translate in a day in an error in the position that would be 11 kilometers per day. So without the general relativistic and special relativistic effects, this would actually invalidate it would turn the GPS useless. Now, again, well, this is very important, but GPS involves satellites. Satellites move at the fastest speed. What about normal speeds? Well, general relativistic effects were measured already in 1971. So Einstein clearly says that time is what is measured by clocks. This is the definition. And so in 1971, Haefele and Keating flew atomic clocks in commercial flights all around the world and proved the relativistic time effects. They measured them, computed them, and the predictions agree with the observation. So this is a modern practical version of the twin paradox. They had two clocks, identical clocks, synchronized. One stayed put, stayed on Earth. The other went in a trip and came back. But in this case, the velocity is just the velocity of commercial airplanes instead of relativistic speeds. But this is a version of the twin paradox. So nowadays, we can do much better. And in 2010, one can measure, and here you can see the reference, Chu et al. In Science, 2010. Gravitational time dilation we can see at the scale of daily life. So here we can see the difference. This is the difference in frequency. So this proves that actually clocks run faster when raised a certain amount, when elevated by a certain amount. In this case, here in the change, when the change of rate in the clock happened, was measured, a clock was elevated by half a meter. So half a meter is about a third of your height. And so now in 2010, we can measure gravitational time dilation when something is moved just by half a meter. So we can see that relativity, the theory of relativity, is not any longer a theory about strange, far away, inaccessible objects, but actually it is something that we have to deal with in our everyday life.